All right, my name is Kosta Derpanis. I'm an associate professor at Ryerson University, and I actually have the daunting task. What I'm going to try to do is I'm going to try to explain computer vision, the what, why, and how in 8 minutes. So the first question that we're confronted with is, what is computer vision? So there's not really one definition, but what I'm going to offer is the following. Computer vision is a study of recovering useful properties of the world from one or more images. So for example, you could take images from multiple viewpoints, or maybe you have a stream of images from a video sequence. But importantly here, with an algorithmic level of specification. So what we want is a sequence of steps that we can actually compute. So our starting point is taking a picture. Okay, so we have the scene over here. We have our camera. A camera is nothing more than a light reading device. So we take our picture over here, and the question is, what's a picture? Well, a picture is nothing more than basically an array of numbers. Each of these numbers, okay, we call these a picture element, or a pixel basically tells us how much light was measured at that particular location. In the case when we have a color image, what we have here is our 3 grids. So we have a grid of red, green and blue, and what it tells us here is how much red, green, and blue are at each location. Now importantly here, I want to stress that an image does not equal understanding. Those numbers alone are just lifeless. What we have is what we call the semantic gap. And the idea here is, how do we go from these lifeless numbers to something meaningful? So the start of our story starts in 1966. So this is a famous technical report from MIT. It was called the Summer Vision Project. And what they thought they would be able to do was solve computer vision in a summer. Now the people at MIT are very smart, and well, they failed. So we spent the last 50 years progressing. So we've made progressions towards solving parts of computer vision, but there's still a lot of work to be done. So next the question is, what makes computer vision hard? So I'm just going to take one part of it, which is the recognition problem. So one problem is, how do we deal with differences of viewpoint? So we have an object, and we're going to capture it from a multitude of views. And if we just look at the raw pixels alone and try to compare them, then the pixels from this particular view and another view will look completely different. Next, we have the problem of intra-class variability. So if we look over here, we have a bunch of dogs, each one looking completely different from the other, but we seamlessly, or at least we believe seamlessly, we can recognize each of these as dogs. It turns out that the human brain actually expends quite a bit of processing in order to deal with this recognition problem. Okay, so that was the variability, or the intra-class variability, but also deformation. So our objects tend to be highly deformable, but nonetheless we recognize this. It's a little bit jarring, but they're dogs nonetheless. Next, the question is, how do we deal with differences in illumination? Okay, so we have our objects, and they also interact with the lighting in the world. Nonetheless, we recognize this as a dog, irrespective of how it's being illuminated. And finally, we have the problem of occlusion. So if we're just given a portion of the object, nonetheless, we recognize this as a dog. We don't have to actually see the whole dog in order to recognize it as a dog. Okay, now we come to the loaded question, which is, how does it work? So how do I summarize 50 years of research in a couple of minutes? Well, you know what? I'm going to start from 2012. So it turns out that 2012 is an important year in computer vision. And in particular here was Geoff Hinton, the so-called godfather of deep learning. Okay, so at this point, Geoff was working outside of computer vision. So the type of things Geoff was doing was not part of the mainstream of computer vision. But Geoff Hinton and his group entered a major image recognition competition. And the story goes on a dare. So that competition was the ImageNet competition. So this was a yearly competition run with all the top groups, both industrial and also academic groups. And the challenge was recognizing 1,000 categories of objects given 1 million images for training. And what Geoff used was something no one was using in the standard computer vision area, which was called deep convolutional neural networks. Graham touched upon it a little bit. I don't have time to really go through it, but the idea is basically going from the raw image and mapping it to one of those 1,000 categories. So over here, I just want to show you a plot of the ImageNet error rate over the various years the competition was run. And 2010, 2011, the error rate was about 30%. These were using standard computer vision techniques at the time. Then we have 2012. They nearly halved the error rate. And this was completely shocking. Some people thought it was even an error, right? But they completely halved the error rate. And then in subsequent competitions, eventually everybody moved towards using deep convolutional networks. So over here, I'm just going to show you a plot. On the horizontal axis, we have the various major conferences, computer vision. And on the vertical axis, we have basically the percentage of papers using deep learning. So if you notice over here in 2013, very few people were using deep learning. But over time, the number of people that have been using deep learning has kept increasing, increasing, and increasing. And I mean, the idea was basically, we had this idea, you know, in computer vision that, well, that's good for image recognition, but it's not going to address my problem. Well, it turns out that this technique is quite general, and we've been able to find ways of integrating it into other techniques. Okay, so the one thing I need to point out here is the big driving force are large collections of images, but also large collections of images with labeled data. Without the label, a lot of the breakthroughs that we have would not be possible. And collecting this data can be very hard, expensive, time-consuming, or depending on the problem, impossible. So what's happening a lot in the computer vision literature and also in the machine literature is the question of, can we start training these networks with smaller amounts of labeled data or no labels at all? So now what I want to do is I want to give you just a sampling of the various applications in computer vision. So one of the big breakthroughs of early computer vision was face detection. So the idea here is that we're given an image, and what we want to do is we want to determine where all the faces are. You can pretty much consider this a solved problem. More recently, this is just a free app. Here what we're trying to do is we're trying to track the various parts of the faces, but not only that, but we're also trying to determine what the emotion of the user is. Okay? So that was detection, and here now what we have is the recognition problem. So the question here is, who is depicted in the picture? Okay? This has started also work now. So what I mean by working is we're seeing it in consumer applications. But I need to point out that there's a growing question about privacy. Okay, so maybe some of you have seen this. This was an article a few weeks ago in China. So apparently the police officers now are wearing glasses that also have cameras, and they're able to recognize who the people are and also the license plates. And you may say, okay, that's in China. Well, it's also happening in our own backyard. So for example, this was also in the news a couple of weeks ago. So in Madison Square Garden down in New York, they're also using similar technology. So there are big questions in terms of privacy with these technologies now that they're working. Another thing I want to point out over here is image recognition. So here's a web page from Google. From Facebook, but Google's doing the same thing. So if we just take a look at the metadata over here. So what I'm going to do is I'm just going to show you a little bit of the metadata of this particular web page, and we're going to zoom in. And what you notice over here, it says, the image may contain one or more people riding bicycles, and outdoor. So a lot of the big companies and also startups have started looking now, how do we start mining the actual image data, both the images and also video. So here's a really fun one. So people are starting to look at full body articulation understanding. So the idea here is, where are all the joints? And this just came out last week from Facebook, or about a month ago from Facebook. It's not only where the joints are, but now they're trying to understand the full body. So another big application is robotics. So here we have a UAV from Skydio. That's a startup, but a lot of people are working on this problem. So here they're looking at a personal UAV that just tracks the person as they navigate through the space. Computer vision will be used here for the navigation system. Autonomous cars, huge application. A lot of work's being done in Toronto and around the world, both by the big automotive companies, but also by many startups. Right? So over here, what I'm going to show you is the view from the car. So basically, the computer vision system is trying to basically determine where all the objects are, where all the people, where all the cars are, where all the pedestrians are, and it's also trying to reason about the geometry in order to determine what that navigatable space is. So autonomous vehicles have the potential to change our lives. So what I want to do here is I want to share this particular stat. So this was from 2010. Unfortunately, I suspect that this number's gone up, but 1.24 million people die each year because of road deaths. And the hope is with these autonomous vehicles that we can drive that number way down. And then here's another stat. Some of you probably can relate to this. So this is a stat related to Toronto. So it turns out that on average, the Torontonians spend about an hour a day in their car. So that's wasted time, but also there's a lot of pollution caused by that. So here's another application, and this is really from Amazon. And what they're trying to do is look at the next generation of shopping, and they're using also computer vision. So the idea is you just walk in, you pick up the product, you put in your bag, and you just walk out. And if you just look at the ceiling of that store, it's just covered with cameras. And what they're trying to do is reason about what the shopper is doing. And the final application I want to point out over here is, can we see this in the back, by the way? Okay, so I want you to look very closely. So this is a health application. So I'm going to play a video now, and I want you to determine or try to figure out whether you see a difference in the image. So the video will start now. Anyone see any differences? Okay, it turns out there are differences, but they are imperceptible. So this is some great work from MIT. So if I play that video again now, what you notice is they're using computer vision in order to enhance those differences. So on the left-hand side over there, you can see the fluctuation of blood in the face. So you can actually measure the human pulse. And if you look closely at the chest of the baby, you can see the respiratory motion. Right? So this is actually quite exciting because we can start looking at building non-invasive devices. So for example, rather than tethering some type of device to the child, maybe that could be dangerous, we can just basically put a camera and just look at the child and measure its heartbeat. Okay, these are exciting times. So I've been working in computer vision since the late 90s, and nothing was working. You know, we had little demos that work in our labs, but what I mean by working is actually seeing products out in the world that work in a variety of situations. So, you know, you just have to look at the media. So New York Times and a bunch of others, and you're seeing computer vision in the headlines. So exciting times. There's also a lot of hype. So over here, I'm just giving you the academic perspective. I was at a conference recently in Europe. I remember the days, and it wasn't that long ago, where there'd be maybe 1,000 people at the conferences. Now the conferences have 5,000 to 8,000. I mean, the organizers are scared that they're just not going to have enough room. Now, the payoffs can be personally lucrative. There are many jobs. I know when I was finishing my PhD, most of the jobs were in the US and also for military contractors. Nowadays, you're seeing a lot of, you know, the usual suspects, the Googles, the Amazons, the Facebooks. These are the big companies, but they're also small companies. So I want to share this stat with you. So it's, there's one stat that says that the computer vision industry will grow from about 6 billion to about 33 billion by 2019. But also the benefits to society can be life-changing. So for example, we're going to, hopefully soon we'll have robots that will take care of our loved ones. We're going to have autonomous vehicles that will drive those deaths down and give us more time to spend also with our loved ones. And finally, we're going to have computer vision that will monitor our health. So I'm done. If you're interested in my research, you can take a look at my webpage. Okay? Thank you.